Hello and welcome to this tutorial on the optocoupler. What we're going to do is we're going to look at why we need them and how they work. So it will be an explanation of both. So the best example of showing you why we need optocouplers is often done in some sort of controller where we have a power rail up here and we are going to convert this into an AC waveform. So let's say, for example, we've got 400 volts DC sitting up here, and we can take that and we can convert that into AC quite easily with a couple of MOSFETs like this, and we'll do it as a three-phase one just for the hell of it. Really doesn't really matter for the purposes of what we're talking about here. Okay, and so we're going to use MOSFETs because they're fastest and easiest and simplest for us to draw. Now, if this is a 400 volt battery and we've got our controller sitting down here, our microcontroller, now you know that in order to turn on a MOSFET we need to put a logic high signal into here, and that needs to be done relative to the source down here. So these are the two connections we put in, and similarly with this one here and for this one here, and also for these other devices over here, which I'm not going to draw into the circuit because it'll just get all confusing. Now, for some of you, you may have already seen a problem here, and the problem is that we're going to blow up our microcontroller. It's going to disintegrate, and the reason for that is because, excuse me while I change pens, here we are. Each of these devices has got a small volt drop across it, and we'll call it 1.5 volts. It's not uncommon to have something along that, a volt drop across it, and at these sorts of voltages. So if we're putting 400 volts in through here, we turn on this device, we drop 1.5 volts across it, which means at this point here we have 385.5 volts. This point down here, this is nominally, people call this positive and negative, this is nominally our ground point here. We now have 385 volts here coming through our device and going out there, that's fine, but we also have this voltage sitting here on this line. So this line coming into our microcontroller is also at 385 volts. This point here, this line coming into our microcontroller, is our negative, or what some people would call ground, or our reference point. So the reality is that across our microcontroller here, we have 385 volts. There are very few little electronic devices, little DIP packages that will handle 385 volts putting across them. And so that's simply going to turn into smoke. Okay? So what we need to do is we need to somehow control both of these without getting this large voltage back in through here. And to do that, we would install some form of isolation in here in order to prevent this voltage being fed back down into here. And the sort of isolation that is typically used nowadays is an Opto Isolator. Now, what the Opto Isolator is it provides isolation optically, and they tend to come in little 4 or 6 or 8 pin packages. They're very simple devices. What they essentially are inside the package is they are an LED and then a photosensitive transistor, often typically they're often drawn as being a N-channel device like that. And what happens inside the package is we would put our signal from our microcontroller here in, our logic output in from our microcontroller here. It's going to draw very low current. The LED inside the package is going to turn on. That's going to energize the base of this transistor, which will therefore pass the logic condition over. As to how these are actually used in reality, what we need to do is we need to do a little bit of conditioning here, not much, fairly minor. What we do, one common way of doing it is this, as I said, this would go off to our micro here. And here's our pin out, our output term pin here, and our ground, our reference point here. And what we would do at this side here is that there would go off to the base of our MOSFET, to the gate of our MOSFET, like that. And this one here would be connected off to our point here, which we will call, it's often drawn as being a ground point or our reference point here. And then one common way of doing it would be to have a pull-up resistor here, like this, going up to our VCC, which, for a decent sized MOSFET was going to be looking at around about 20 volts. Doesn't have to be, but whatever. So what happens here is when we get a logic 1 coming out of here, that is going to turn on our LED, which in turn will turn on activate the base of our transistor, which will turn this device on. What that does is that will drag the gate of the MOSFET down to this voltage. So logic 1 out of here actually means a logic 0 there. So they act as an inverter as well. This is an important thing to note. When we have a logic 0 here, the device is turned off, which means this is turned off, which means that this here, base of the MOSFET, is pulled up through the pull-up resistor, and we end up with a logic 1 here, as I said, an inverter. So if that's going to be our input waveform, this will be our output. Okay, that acts as an inverter, but the important thing is it provides a pathway for the control, the logic, for getting through to here, whilst also isolating everything this side from whatever's going on this side. Now, opto isolators are great. They're wonderful things. They work really well, but they do have some limitations. One of the limitations is that these tend to work quite slowly. So whilst I've drawn this as being an ideal, in reality, our input, if I draw it like this, if I say that this is what our input is, our output is inverted, but also a little bit sluggish. So we often have a bit of a rise time issue and a fall time issue. So you would end up with something like this. Okay, and so here is our time delay that we occur here. Now, if you're switching these things quite slowly, this is not a problem, but if you're switching them quite fast, it could be our rise time and our fall time. So in order to solve this problem here, you might then have to, after the optocoupler, run it through a Schmitt trigger or something like that, and most of you are familiar with what Schmitt triggers are. They're quite simple. They're often drawn as being a basic logic signal, and their symbol tends to look a little bit like that. That's the signal, the symbol there, and what they do is they have a threshold detector. So if they get an input signal that looks like this, they won't turn on until it exceeds a certain point, and they won't turn off until it goes past a certain point. So what they'll do is they'll wait until it here, and then once it gets to here, it'll turn on, and it won't turn off until it drops below this certain point here. So the Schmitt trigger will take this sort of waveform here and convert it back into something that's more better here. That's an adjunct to what we've been talking about. The optocoupler is this part here. We've got electrical isolation from the output to the input, so we don't have this problem. They basically pass a logic condition through the optocoupler with no bad feedback coming this way, and their primary negative consequence is they're a little bit slow to switch. They can take a little bit of time. And if you're only switching at 5, 10, 15, maybe 20 kilohertz, that's not a problem. But if you want to try and switch at 150, 200, 250 kilohertz or any high frequency, this can be a problem, and then you have to correct for it, usually by using a Schmidt trigger. So that's the optocoupler. Thank you for watching. I look forward to seeing you again later. Bye.